Greetings! In this lesson, we're going to split into 2 days for lesson 7.3 with solving trig identities. We've already been kind of creating our own identities, if you will, when we were asked to simplify the trig identities themselves. In this particular lesson, there's going to be a left side equal to the right side. And our goal is to try to get from one side to the other to prove that they're equivalent to one another. And there's 2 ways in which we can do this. We can start on either side of the equation and try to obtain the other, or we could work each side separately until we arrive at the same equivalent expression. And I'm going to show you how to do both of those. Here are some helpful hints before we get started. Either method 1 or method 2 will work. Don't try to do method 1 or method 2 at the same time. Try one, and if it's not working, try the other. Work with the more complex side first. Carry out any algebraic manipulation such as adding, subtracting, multiplying, or factoring is one that we almost forget sometimes. When rational expressions are involved, multiply by forms of 1 so that we can obtain that common denominator. And we've already been doing this part here, but converting to sines and cosines also is very helpful. And if anything fails, just try something. Try something out to see what might work. Our first example is to prove the identity 1 plus sine of 2 theta is equivalent to sine of theta plus cosine of theta squared. We're going to use method 1 by starting with one of the sides. And in this particular instance, I'm going to start with the right-hand side here and see if I can't find and make that equivalent to the left-hand side. So starting with sine theta plus cosine of theta squared, we know that that is equivalent to sine of theta plus cosine of theta times itself. Then when we FOIL or multiply, we will have sine squared of theta plus sine of theta cosine of theta. Now when I go to multiply the insides, notice I'll have cosine times sine. I'm going to just rewrite it as sine of theta times cosine of theta, just so that it's easier to combine like terms here in the next step. And we know that when we multiply, it doesn't matter if we multiply sine then cosine or cosine then sine, they still mean the same thing. And then finally, cosine squared of theta. Combining like terms in the middle here, we have 2 sine of theta cosine of theta with the sine squared of theta in the front and the cosine squared of theta in the back. I also know that when I have sine squared of theta plus cosine squared of theta is equal to 1 because of the Pythagorean identity. So I will replace sine squared of theta plus cosine squared of theta with 1. I know that I have my 1 here in my original, but now I need sine of 2 theta. Well, I have 2 sine of theta cosine of theta, and using my double angle identity, I can replace my 2 sine of theta cosine of theta with sine of 2 theta. And now I've proven that sine of theta plus cosine of theta squared is equal to 1 plus sine of 2 theta. We could, here we worked from the right side to the left, we could start on the left side and work to the right side. I can replace 1 plus sine of 2 theta with its double angle identity, so 1 plus 2 sine of theta cosine of theta. Utilizing my 1, I could replace 1 with my sine squared of theta plus cosine squared of theta, and then factored to give us sine of theta plus cosine of theta squared. This second way would have taken a little bit more creativity to get there, but it can be done. Let's look at another example. And it looks like it's on the previous page. So I'll just write it up top here. It's asking us to prove the identity of sine squared of x times tangent squared of x equals tangent squared of x minus sine squared of x. This particular one, I'm going to work with each side separately using method 2, so working both sides until I can't go any further to see if we can't make them equivalent to one another. So I'm going to start with sine squared of x times tangent squared of x, which I know I can replace tangent squared of x with sine squared of x over cosine squared of x. Multiplying my numerators together, I have sine to the 4th of x over cosine squared of x. Not much more we can do. But maybe we could get the right-hand side equivalent to what we found the left-hand side equivalent to. So let's look at the right-hand side. With the right-hand side, I have tangent squared of x minus sine squared of x. And we're going to, again, replace tangent with sine over cosine minus sine squared of x. Well, in order to add these together, we would need to multiply the right-hand side by cosine squared of x over cosine squared of x so that we have a common denominator. This would then provide us with sine squared of x over cosine squared of x from the left minus sine squared of x cosine squared of x all over cosine squared of x. We've now created a common denominator, which will give us sine squared of x minus sine squared cosine squared of x all over cosine squared of x. In my numerator, notice that they both have a sine squared of x, so I'm going to factor the sine squared of x out, which will leave me with sine squared of x times 1 minus cosine squared. I know that 1 minus cosine squared is sine squared of x because of the Pythagorean identity. Replacing 1 minus cosine squared of x with sine squared of x and multiplying together gives me the left-hand side that we found with sine 4x over cosine squared of x. So since they are the same expression on the left and on the right, we have actually proven the identity. Prove the identity of sine of 2x over sine of x minus cosine of 2x over cosine of x is equal to secant. The left-hand side looks much more difficult than the right-hand side. There's a lot more going on. So I'm going to use method 1 and start on the left side and see if I can't make it equivalent to the right-hand side. Notice in both of our numerators we have double angles. I'm going to replace both of my numerators with their equivalent double angles and see what we can do. Replacing sine of 2x with 2 times sine of x cosine of x still over sine of x minus, I'm going to replace cosine 2x with cosine squared of x minus sine squared of x over cosine of x. This allows me on the left-hand side to have a common factor that we can eliminate since we're only in multiplication on the left. The only thing I have left on the left-hand side is 2 cosine of x minus the entire right-hand side. But in order to combine these fractions together, we need to have a common denominator. So I'm going to multiply by that common denominator of cosine of x. When I multiply cosine of x times 2 cosine of x, we'll have 2 cosine of x squared, or 2 cosine squared of x, all over cosine. And since they're both over cosine, we can then combine them together. Notice so that I'm subtracting the entire right-hand side. So I'm subtracting cosine squared of x, and when I subtract a negative sine squared of x, that turns into a positive sine squared of x. On the top, we're able to combine like terms because notice we have cosine squareds of x and combine like terms. So if we had 2 cosine squareds and I subtract 1 cosine squared, we now have only a single cosine squared of x plus sine squared of x. And again, we have our Pythagorean identity, which means that I can replace cosine squared of x plus sine squared of x with 1. And 1 over cosine of x is equal to the secant of x that we were looking for. So we have proven this identity. I'm coming to the end of this page. I'm just going to rewrite this next one on the top for our next example. We're looking to prove the identity, and our identity is secant of t minus 1 over t secant of t minus 1 equals 1 minus cosine of t over t. What we cannot do is say, oh, here's a secant of t and here's a secant of t. We cannot do that. We cannot do that because secant of t on the top has the subtract 1 and they're connected together. So we can't just go ahead and subtract things away like that. They have to be factored in order to do so. I'm going to use method 1 by starting on the left-hand side. I'm going to convert my secants into cosines. I'm going to turn secant of t on the top with 1 over cosine of t minus 1 all over t times 1 over cosine of t. Now that I have a complex fraction, I can multiply by the reciprocal. So this is going to be equal to the entire top multiplied by the reciprocal of t over cosine of t, so cosine of t over t. I'm now going to go ahead and multiply to eliminate my parenthesis here. When I multiply 1 over cosine of t times cosine of t over t, I'll have cosine of t over t times cosine of t minus cosine of t over t when I multiply it by 1. Notice that because now we are in factored form, I am able to eliminate this portion here. This gives me 1 over t minus cosine of t over t. And since they have the same denominator, we're able to combine them to be 1 minus cosine of t all over t. And we ended up with the right-hand side, so we know we are finished. This next example, we have cotangent cosec plus cosecant equal to sine over 1 minus cosine. We're going to use method 2 in this example. I'm going to start on the left-hand side by converting my cotangent and cosecant into cosines and sines. Cotangent is cosine over sine, and cosecant is 1 over sine. Well, they have the same denominator, so I can rewrite it as cosine plus 1 over sine. However, we're kind of stuck at this point. So since I'm stuck, I don't really have anything else I can do here. Let's move to the right-hand side and see if we can't get the right-hand side to equal what we simplified the left-hand side to be. So starting with sine over 1 minus cosine, I'm going to multiply the denominator by 1 plus cosine over 1 plus cosine. So I'm going to multiply it by a version of 1. You're going to see why here in a second. So I'm going to be a little creative when I do this. When I multiply my numerator and my denominator by 1 plus cosine of theta, knowing that I need a sine in my denominator here, I'll still have sine times 1 plus cosine, but in my denominator though, when I FOIL my denominator, I'll have 1 plus cosine minus cosine minus cosine squared. In our middle, we create a 0 pair, and I'm left with 1 minus cosine squared. I know that 1 minus cosine squared is equal to sine squared because of the Pythagorean identity. I'll replace 1 minus cosine squared with sine squared, so nothing changed on the top. Now that I'm in multiplication, I'm able to eliminate a sign from the numerator and a sign from the denominator, providing me with 1 plus cosine over sine. And now we have the exact same expression on the left side as we do the right side. So we have proven the identity. Example 6 is 1 plus tangent of x over 1 plus cotangent of x equals secant of x over cosecant of x. I'm going to work this working the left side and the right side together to see if we can't find some common ground. Looking and starting on the right hand side, I'm going to turn this into sines and cosines. That will provide me with 1 over cosine of x over 1 over sine of x. Multiplying by the reciprocal, I'll have 1 over cosine times sine of x over 1. And when I multiply these together, I end up with sine over cosine, which is tangent of x. So the left-hand side is tangent. Let's see if we can't get, the right-hand side is tangent. Let's see if we can't get the left-hand side to also be tangent. I'm going to replace my tangents and cotangents with sines and cosines. On the left, then I'll have 1 plus sine of x over cosine of x all over 1 plus cosine of x over sine of x. In order to combine like terms on the left, I'll have to, on the top, I should say, I'll have to multiply by cosine. Cosine over cosine. And on the bottom, I'll have to multiply by sine over sine. In my numerator then, I will have cosine of x plus sine of x all over cosine. In my denominator then, I'll have sine of x plus cosine of x over sine of x. Now we'll go ahead and multiply by the reciprocal to get rid of our complex fraction here. I'll have cosine of x plus sine of x over cosine times multiply by the reciprocal, so sine of x over cosine of x plus sine of x. So notice that these are in its factored form, and the top left and the bottom right are the same factors, so that's allowing us to eliminate them. And then all I'm left with is sine of x over cosine of x, and we know that is the same as tangent of x, and since we have the left side equal to the right side, we are complete. In example 7, we have secant of 2x equal to secant squared of x over 2 minus secant squared of x. Let's start on the left-hand side. I've got a double angle here. Let's see if what we can do with this portion. The double angle is the same as 1 over cosine of 2x. And I know that I can replace cosine of 2x using that double angle with 1 over cosine squared of x minus sine squared of x. Now, that's not the Pythagorean identity, so at this point we're kind of stuck. So I'm going to stop here on the left because I'm going to say I'm stuck. So when I'm stuck, then I'm going to move to the right-hand side and see what I can do on the right-hand side. I'm going to replace secants with tangents utilizing the Pythagorean identities. So I'm going to replace secant squared with 1 plus tangent squared of x. And I'm going to do the same in my denominator. I'm going to say 2 minus and replacing secant squared with 1 plus tangent squared of x. At this point, I can eliminate my parentheses by actually subtracting, and 2 minus 1 would just be 1, so I'll still have 1 plus tangent squared of x over 1 minus tangent squared of x. That would be the same then as 1 plus sine squared of x over cosine squared of x, and 1 minus sine squared of x over cosine squared of x. In order to combine them together, what we'll need to do is multiply this 1 by cosine squared of x over cosine squared of x, and the same on the bottom to have a common denominator. That will then provide us with cosine squared of x plus sine squared of x all over cosine squared of x, all over cosine squared of x minus sine squared of x over cosine squared of x. In order to eliminate our complex fraction here, we're going to multiply by the reciprocal. So I'm just going to rewrite my top part of the fraction and multiply by the reciprocal of cosine squared of x minus sine squared of x. You might be able to see where we're going with this at this point. Over, multiply by the reciprocal. Cosine squared of x over cosine squared of x minus sine squared of x. We have a common factor when we're multiplying, and I also know that cosine squared of x plus sine squared of x using Pythagorean's identity is 1. So 1 over cosine squared of x minus sine squared of x. And I've found then that my left-hand side where I got stuck equal to my right-hand side. And so now I know that I've proven this particular identity. Our last example is 1 minus cosine of 5 theta times cosine of 3 theta minus sine of 5 theta sine of 3 theta equal to 2 sine squared of theta. I'm going to use my my sum identity on the right-hand side because it looks very familiar. But first what I'm going to do is factor out the negative. So this is going to take a little bit of creativity, but we'll get there. So I'm going to say this is the same as 1 minus cosine of 5 theta cosine of 3 theta plus sine of 5 theta sine of 3 theta. Now this looks like my sum identity on the right-hand portion of it. So using my sum identity, I'm going to replace this entire piece here with 1 minus cosine of 5 theta minus 3 theta. Well, I can then take 5 minus 3, which we know is 2 theta, and we're getting closer to the right-hand side. And I have a double angle now. I'm going to use my double angle with cosine and rewrite it as 1 minus 2 sine squared of x. Distribute my negative, so be careful when writing these with your negatives. 1 minus 1 plus 2 sine squared of x. Oh, I'm sorry, we're in thetas, not x's. Let's replace those. Well, 1 minus 1 turns to 0, and I'm left with 2 sine squared of theta. And we've gotten the left-hand side to match the right-hand side. And so we're done.